Welcome. In this video, we are doing a complete deep dive into FastAPI, the Python web framework that brought async first API development, automatic documentation, and Pydantic-powered type safety to the Python world. We go from the basics all the way to production deployment, WebSockets, JWT auth, async databases, testing, and Docker. Let's get into it. Next, FastAPI is a modern, high-performance Python web framework for building APIs using Python type hints. Let's unpack that sentence. Modern. It was created in 2018 and was designed from the ground up for the Python 3.6 Plus type annotation system. It doesn't carry 20 years of legacy decisions. High performance. And this is not marketing. Benchmarks consistently place FastAPI among the fastest Python frameworks, competing with Go and Node.js for raw throughput. The reason is its ASGI foundation and native async/await support, which we'll cover in detail. Click. The core philosophy breaks down into three fasts. Fast to run. Performance is a first-class concern. Fast to code, type hints, and editor auto-completion mean fewer bugs and less time looking things up. Studies referenced in the FastAPI docs suggest 200 to 300% development speed improvement and roughly 40% fewer bugs. And standards-based FastAPI implements OpenAPI, JSON schema, and OAuth 2 correctly out of the box. You don't bolt on documentation after the fact, it generates itself. Click. FastAPI was created in 2018 by Sebastian Ramirez. It sits on top of two libraries, Starlet for the ASGI web layer, and Pydantic for data validation and serialization. We'll see how these two underpin everything FastAPI does. Click. Who uses it? Microsoft, Uber, Netflix, Apple, NASA, Explosion AI, the creators of Spacey, all run FastAPI in production. It's not a toy framework. Beat on the right, the mind map captures the four pillars: performance through async and ASGI, validation through Pydantic and type hints, automatic API docs through OpenAPI and Swagger UI, and features like dependency injection, OAuth 2, WebSockets, and background tasks. Next, let's benchmark FastAPI against the frameworks you're likely choosing between. Performance. FastAPI is rated excellent. It is genuinely one of the fastest Python frameworks. Django REST framework and Flask are good. They're synchronous WSGI frameworks built for solid throughput but without native async. Express in Node is also excellent, in the same tier as FastAPI. Async native. This is the big one. FastAPI is fully async native. DRF has partial support that was retrofitted. Flask has no native async. Every request blocks a thread. FastAPI was designed around async from day one. Auto API docs. FastAPI is the only Python framework with built-in automatic Swagger UI and redoc generation. With Django REST framework, DRF Spectacular is a third-party add-on that requires configuration. With Flask, you're on your own. Data validation. FastAPI uses Pydantic, arguably the best data validation library in the Python ecosystem. DRF has its own serializers which are good but verbose. Flask has nothing built in. Type safety. FastAPI gives you full type safety end-to-end through Python type hints. That means your IDE knows the shape of every request and response object. Click. The conclusion is clear. Choose FastAPI when you are building APIs, microservices, or any service where performance, type safety, and auto-generated documentation are important. If you need a built-in admin panel and full-stack features, Django is still the better choice there. Next, let's understand the full architecture before we write any code. Click. Start from the top of the diagram. A client sends an HTTP request. It arrives at Uvicorn, the ASGI server that runs your FastAPI application. Uvicorn is the async web server. FastAPI itself is not a server, it's an application. Uvicorn handles the raw TCP, HTTP parsing, and async event loop management. From Uvicorn, the request enters the middleware stack, a chain of pluggable processors that run before and after your application logic. Cores, authentication tokens, request timing, compression, all handled here. The API router then does path matching. It reads the URL and HTTP method, finds the registered path operation function, and dispatches to it. Before the path operation function runs, FastAPI's dependency injection system resolves every declared dependency, database sessions, current user, permissions, and injects them into the function. Pydantic then validates the incoming request, path parameters, query parameters, request body. If anything fails validation, a 422 error is returned automatically. You never have to write that error handling yourself. The path operation function runs your business logic, queries the database, or calls external services, and returns a result. On the way out, Pydantic serializes the return value according to the declared response underscore model, filtering fields and validating types before it becomes JSON. Click. The two foundation libraries in brief. Starlet provides the ASGI toolkit, requests, responses, routing, middleware, WebSockets, background tasks. Pydantic v2 provides everything: data-related, validation, serialization, JSON schema generation, settings management. Click the formula, FastAPI equals Starlet, plus Pydantic, plus automatic OpenAPI generation. Everything else is built on those three pillars. Now let's trace a real request through the complete lifecycle using the sequence diagram. A client sends an HTTP request to Uvicorn, the ASGI server. Uvicorn fires up the ASGI scope, a dictionary describing the connection, and passes it into the middleware chain. Middleware processes the request going in, setting headers, validating API keys, recording start time. It then calls into the router, which pattern matches the URL and HTTP method and identifies the target path operation. The dependency injection system activates next. FastAPI inspects the function signature, sees every depends, annotation, resolves the dependency graph, which can be many levels deep, and prepares all the injected values. With dependencies resolved, the function is called. Pydantic parses and validates all incoming parameters. Path parameters are coerced to the declared types. Query parameters get their defaults applied and constraints checked, and the request body is deserialized and validated against the input schema. The validated Python objects are handed to the path operation. The path operation awaits its database query. The await keyword here is crucial. While waiting on the database, the event loop is free to process other incoming requests. This is the source of FastAPI's concurrency advantage. The result comes back from the database. The path operation returns it. Pydantic serializes it into JSON according to the response model. The middleware processes the response going out, and Uvicorn sends the final HTTP response back to the client. Every request, every time in this order. Knowing this lifecycle is your map for debugging any FastAPI problem. Let's look at how to structure a real FastAPI project. Starting with the install. Pip install FastAPI Uvicorn. Standard. The standard extra pulls in UV loop, HTTP tools, and WebSocket support. Add SQL Alchemy, Alembic, and Pydantic settings for a full production stack. Click Here's the directory layout I recommend for anything beyond a simple script. At the root, main.py is the app factory. It creates the FastAPI instance and registers all routers. The core/directory holds cross-cutting concerns: settings.py for Pydantic-based configuration, security.py for JWT, and password hashing utilities. The API/v1/directory holds route handlers organized by resource, users.py, posts.py, auth.py. Versioning your API directory from the start costs nothing and saves enormous pain when you need to ship a breaking change. The model/directory has your SQL Alchemy ORM models, the database schema layer. The schema/directory has your Pydantic models, the API request and response shapes. These two are separate because the database representation of data and the API representation are often different. The CRUD/directory holds reusable database access functions, the create, read, update, delete operations called by your route handlers. The DB/directory manages the async engine and session lifecycle. Dependencies.py has your shared FastAPI dependencies. Tests/holds your PyTest suite. Click the key insight in the right-hand table. Models/ is SQL Alchemy for the database. Schemas/ is Pydantic for the API. They serve different masters and should be kept separate. Next, let's look at a real main.py, the application entry point. We create the FastAPI instance and pass metadata, title, description, version. These feed directly into the auto-generated Swagger documentation. The @async context manager lifespan function is modern FastAPI's startup and shutdown hook. Code before the yield runs its startup. Initialize your database connection pool, load a machine learning model, warm up a cache. Code after yield runs at shutdown. Close connections, flush buffers. This is cleaner than the older on_event approach and works correctly with PyTest fixtures too. We then call app.include_router 3 times, once for auth, once for users, once for posts, each with a URL prefix and a tag. The prefix sets the URL route for all routes in that router. The tag groups all those routes together in the Swagger UI. This is how modular FastAPI applications scale. Each router is its own file. The app just aggregates them. Click the 3 commands at the bottom. Run Uvicorn main app. Reload for development. The reload flag watches for file changes and restarts automatically. After startup, visit /docs for the interactive Swagger UI and /redoc for the read-only redoc reference. Both are auto-generated, 0 configuration. Click the key architectural point. FastAPI runs on ASGI. WSGI, what Django and Flask use, is synchronous. One request blocks one thread. ASGI is asynchronous. One worker can handle thousands of concurrent connections by yielding the event loop during I/O waits. That's the fundamental performance difference. Next, a path operation is FastAPI's term for a route handler, a function decorated with an HTTP method decorator and a URL path. Let's walk through a complete CRUD router for blog posts. The API router instance is a mini application that holds a group of related routes. We'll mount it on the main app with a prefix. At router.get with response_model equals list post out. This is a list endpoint. FastAPI will call the function, take the return value, validate it against post out, and serialize it as a JSON array. The depends get_db injects an async database session automatically. At router.post, creates a new post. Notice status_code equals status. HTTP_201_ created. This tells FastAPI to respond with HTTP 201 instead of the default 200. We inject both get_db and get_current_user. The current user dependency ensures this route requires authentication. At router.get/post_id takes a path parameter. If the post isn't found in the database, we raise HTTP exception, status_code equals 404. FastAPI catches that and converts it to a proper JSON error response. At router.patch/post_id handles partial updates. The client only sends the fields it wants to change. The post update schema has all fields optional. At router.delete/post_id with status_code equals 204 to 204. No content means success with no response body. Click. The diagram maps this to the HTTP verbs, green for get, purple for post, blue for patch, red for delete. All mounted under the /posts prefix defined when we include the router in main.py. Click. The 6 HTTP method decorators are listed on the right. One important nuance. Put means full replacement of the resource. Include every field. Patch means partial update. Include only the fields you're changing. Use them correctly. Next, FastAPI extracts request parameters from 3 locations: the URL path, the query string, and the HTTP headers. Let's look at each. Path parameters are embedded in the URL pattern with curly braces. gh/posts/42. The 42 is the path parameter. We declare it in the function signature with the same name and a type annotation. FastAPI automatically coerces the string 42 to an int. We use annotated with path to add metadata. ge=1 means the value must be greater than or equal to 1. FastAPI validates this and returns a 422 if it fails. Query parameters are appended after the in the URL. geatis/posts, skip equals 0, and limit equals 10, and status equals published. We declare them in the function signature. Any parameter not in the path is treated as a query parameter. Query, ge=0, default equals 0, sets both a validation constraint and a default value. str, none equals none, makes the parameter optional. The min_length equals 3 on Q means if the search term is provided, it must be at least 3 characters. Header parameters are injected via header. FastAPI automatically converts header names. HTTP headers use X token. Python converts it to X_token. Hyphens become underscores. User agent becomes user_agent. Click. The diagram shows the 3 extraction paths clearly. The raw URL and headers come in. FastAPI routes each value to the correct extraction function, and they all arrive at the path operation as validated, typed Python objects. Click. The validation constraint list is your toolkit. GEGT-LT for numeric bounds, min_length, max_length for strings, pattern for regex validation. All declared inline, all enforced automatically, all documented in Swagger UI without any extra work. Next, Pydantic schemas are the data contracts of your FastAPI application. They define exactly what shape data must take when coming in and going out of every endpoint. The pattern I use, and that most production FastAPI projects converge on, is the base, create/update/out hierarchy. Postbase holds the shared fields and validation logic. The title field uses field. The ellipsis makes it required, with min_length equals 5 and a description that shows up in Swagger. We define a @field_validator for the title. The @class method decorator is required by Pydantic version 2. It runs after basic type coercion and before the model is considered valid. We strip whitespace and raise a value error if the result is empty. PostCreate inherits from Postbase and adds category_ID, the only additional field the client sends when creating a post. PostUpdate is flat, not inheriting from base. All fields are optional because patch means send only what you're changing. A client might send just status published and nothing else. PostOut is what the API returns. It extends the base with id, author_id, timestamps. The crucial addition is model_config equals from underscore attributes, true. This is Pydantic v2's ORM mode. Without it, Pydantic can only read from dictionaries. With it, it can read attributes off SQL Alchemy model instances, which is how the ORM objects returned by the database get serialized to JSON. Click the diagram shows the flow. Create and update schemas flow inward from client to endpoint. Out schema flows outward from endpoint to client. Base sits at the top, providing shared logic to both. Click key field, behaviors field, means required. Field, default smiley face or field none, means optional. Min_length, max_length, GE, L pattern, all Pydantic v2 field constraints. Examples equals populates the Swagger UI example values. Description equals adds docs. Next, let's go deeper on Pydantic's validation pipeline. Understanding this saves you enormous debugging time. The user create schema demonstrates the full pipeline in one class. We have email str, a Pydantic type that validates email format using the email validator package. Password has a minimum length of 8 enforced at the field level. Password_confirm is for the match check. At field_validator, username runs after the field's type coercion. We check if it's alphanumeric. If not, we raise a value error. We lowercase it and return the cleaned value. The return value from a validator replaces the original. At field_validator password checks password strength, at least one uppercase letter, at least one digit. These are simple rules, but they show you can write arbitrarily complex validation logic. At model_validator, mode equals after, runs last, after all individual field validators have passed. At this point, self.password and self.password_confirm are both available as validated values. We compare them. If they don't match, we raise a value error, which becomes a proper validation error in the 422 response. Click the pipeline diagram traces the flow. Raw JSON comes in, gets coerced to Python types, runs through per field validators, then the model level cross-field validator, and if everything passes, produces a clean validated Python object ready for your function. If anything fails at any stage, FastAPI automatically returns a 422 response with a structured error payload. The lock tells you which field failed, MSG tells you why. Click that last point is worth emphasizing. You write no error handling code for validation. FastAPI and Pydantic handle the entire 422 pipeline automatically. Zero boilerplate. The response_model parameter on a path operation decorator does three things. It filters the response to only include the declared fields. It validates that the return value actually matches the schema, and it documents the response shape in Swagger UI. Look at get_user. The function returns a SQL Alchemy ORM object, a Python class with many attributes, including potentially hashed _password. The response_model equals userout tells FastAPI to pass that object through Pydantic's userout schema. Only the fields declared in userout are included in the JSON response. The hashed password never leaks to the client, even if the ORM object carries it, because userout simply doesn't include that field. This is your first line of defense against accidentally exposing sensitive data. Status_code equals status. HTTP_201 created on the create endpoint changes the HTTP status code from the default 200 to 201. Always use the status module constants rather than magic numbers. It's self-documenting and avoids typos. Response_model_exclude equals hashed_password is _superuser is an explicit exclusion set that strips those fields even if they appear in the response model. Useful when you want to use the same schema in multiple places but exclude certain fields in specific contexts. Status_code equals 204 on the delete endpoint. 204 means success with no content. No body is sent. We return a bare response, status_code equals 204, to signal that explicitly. Click the serialization pipeline diagram makes the flow clear. The ORM object flows into Pydantic's response model, gets filtered, validated, and serialized to JSON, with the declared status code applied before it leaves FastAPI. Click the status code reference on the right is your quick guide. 200 for reads, 201 for creates, 204 for deletes, 400 for bad client input, 401 for unauthenticated, 403 for unauthorized, 404 for missing resources, 422 for validation failure. Next, FastAPI's dependency injection system is one of its most powerful features, and once you understand it, you'll use it for almost everything. A dependency is just a callable, usually a function, declared with depends, in a path operations signature. FastAPI calls it, gets the result, and passes it into your function. That's the whole idea, but the implications run deep. Look at get_db. It's an async generator function. It yields an async session. FastAPI calls it, gets the session, and when the request is finished, resumes execution past the yield, committing on success or rolling back on exception. A database session is created per request, used throughout the request, and cleaned up automatically. No manual session management anywhere in your route handlers. Get_current_user depends on two things: the OAuth2 scheme, which extracts the JWT from the authorization header, and a database session from get_db. It decodes the JWT, looks up the user, and returns the user object. Any route that declares depends, get_current_user, gets the authenticated user injected and is automatically protected. If the token is invalid or expired, the dependency raises a 401 before your route handler ever runs. Require_admin builds on get_current_user. It depends on a dependency that itself has dependencies. FastAPI resolves the full graph. The admin stats route just declares depends, require_admin, and gets a verified admin user injected, without any auth logic in the route itself. Click the dependency graph on the right, makes this concrete. Admin_stats depends on get_db, and require_admin. Require_admin depends on get_current_user. Get_current_user depends on the OAuth2 scheme, and get_db again. FastAPI resolves all of this, caches get_db so the same session is used, and calls each dependency once per request. Click 4 reasons this pattern is excellent. Automatic resolution, per request caching, so get_db isn't called twice. Full testability via app.dependency_overrides. You can swap any dependency with a mock in tests, and shared resources defined in one place and reused everywhere. Next, FastAPI's security utilities implement OAuth2 password flow and JWT authentication correctly. Let's build the complete auth stack. In core/security.py, we set up 3 things. First, a crypt context from passlib configured for bcrypt. This handles password hashing and verification. #password takes a plain string and returns a bcrypt hash. Verify_password checks a plain password against a stored hash. Never store plain passwords, only the hash. Second, OAuth2 password bearer. This is a FastAPI security utility that reads the authorization, bearer less than token greater than header from incoming requests. You give it token URL pointing to your login endpoint. FastAPI uses this to generate the correct Swagger UI auth flow. Third, the JWT utilities. Create_access_token takes a dictionary, adds an expiry timestamp, and signs it with the secret_key using the HS256 algorithm, returning a compact JWT string. Decode_access_token verifies the signature and returns the payload, or none, if the token is invalid or expired. In the login endpoint, we look up the user by username, verify the password with verify_password, and if both checks pass, call create_access_token with the user ID as the subject claim, and return the token. Click the sequence diagram tells the full auth story. Client posts username and password to /auth/token. The endpoint verifies the credentials and returns a JWT. The client stores it. For every subsequent request, the client sends the JWT in the authorization bearer header. The protected route triggers get_current_user via DI, which decodes the token and loads the user from the database. If valid, the route runs. If not, a 401 is returned. Click the JWT structure. A JWT is 3 base 64 URL encoded sections separated by dots: header, payload, signature. The payload carries the subject, your user ID, and express, the expiry timestamp. The critical point: base 64 encoding is reversible. Anyone can decode the payload and read it. Never put sensitive data, passwords, credit card numbers, secrets, in the JWT payload. Sign it yes. Encrypt it no, unless you specifically use JWE. Next, FastAPI pairs naturally with SQL Alchemy 2.0's new Async API. Let's build the full database layer. In db/session.py, we create an async engine using the ASYN-CPG driver for PostgreSQL. Note the PostgreSQL plus ASYN-CPG : connection string. We configure a pool size of 10 simultaneous connections shared across all concurrent requests. Async_session maker creates a factory for async sessions. The post model in models/post.py uses SQL Alchemy 2.0's new map type annotation syntax. Mapped means a column that holds an integer. Mapped_column, primary_key equals true, configures it as the primary key. Mapped_tr gives us string columns. Mapped datetime maps to a timestamp column. The relationship, with back_populates, creates the bidirectional ORM relationship to the user model. The CRUD/post.py functions are async. Get runs a select post.where post.id == id. This is SQL Alchemy 2.0's new core expression syntax, fully type-safe. Await db.execute sends the query scalar _1_ or none, returns either the single matching post or none. Get _multi-chains offset limit and order _by for pagination. Create uses model _dump to convert the Pydantic schema to a dictionary, constructs the ORM object, adds it to the session, and flushes, which writes to the database within the current transaction without committing. Click architecture diagram shows the complete async chain, app to engine to connection pool, to session maker, to CRUD functions, to ORM models to PostgreSQL. Every hop is async, nothing blocks a thread. Click the async driver choices at the bottom. PostgreSQL uses ASYN-CPG, the fastest async PostgreSQL driver in Python. MySQL uses AIO MySQL. SQLite uses AIOSQL. For NoSQL, Motor for MongoDB and Redis PY in async mode for Redis. Next, Alembic is the migration tool for SQL Alchemy. It tracks schema changes and applies them to the database. It works with async SQL Alchemy with a small setup adjustment. The workflow is straightforward. Define your SQL Alchemy models. Run Alembic revision. Autogenerate -m add posts table. Alembic inspects the difference between your current models and the last migration state, and generates a Python migration file describing the changes. Then Alembic upgrade head applies all pending migrations. When you modify a model, say, adding a status column, run make migrations again, get a new file, run migrate. Each file is numbered and stored in versions, /. This is your schema's Git history. Alembic downgrade -1 rolls back the most recent migration. Alembic history shows you the full chain. Click the workflow diagram shows this cycle visually. Model change, generate migration file, apply to database, repeat. It's the same DRY loop as Django migrations, but for the SQL Alchemy world. Click the version chain diagram shows the dependency graph. 0001 _ initial to 0002 _ add _status to 0003 _ add _tags to head. Alembic always knows which migrations have been applied and which are pending. In CI/CD, Alembic upgrade head is typically the first command run on deploy, auto-applying any new migrations before the app starts. Async/await is the foundation of FastAPI's performance claim. Let's understand exactly what it means and how to use it correctly. The basic pattern. You declare path operations with async def. Inside, every I/O call is prefixed with await. When execution hits an await, Python suspends that coroutine and yields control back to the event loop. The event loop is free to start or resume another coroutine, handling another incoming request, for example. When the awaited I/O completes database returns results, external API responds, the event loop resumes the original coroutine from where it left off. Async CIO.gather is the power move. Look at the dashboard endpoint. Instead of awaiting 3 database queries sequentially, query 1, wait, query 2, wait, query 3, wait, we fire all 3 simultaneously with gather. Python starts all 3 coroutines, then yields the event loop to whatever can proceed. The total time is the duration of the longest query, not the sum of all 3. For an endpoint that hits multiple data sources, this can be dramatically faster. For external HTTP calls, use httpx.async client. The synchronous request library blocks the thread. It cannot await. HTTPX is the async native drop-in replacement. Click the side-by-side diagram captures the fundamental difference. Traditional sync, request 1 arrives, thread blocks on database, nothing else runs, request 2 has to wait. Async, request 1 awaits database, event loop immediately picks up request 2 and request 3. When the database responds to request 1, the event loop resumes it. All 3 requests progress concurrently on a single thread. Click the operational rule. Use async def for I/O bound work, database calls, HTTP requests, file reads. Use regular def for CPU bound work, image processing, data crunching. FastAPI automatically runs regular def functions in a thread pool via run_in_thread pool, so they don't block the event loop. Never call a blocking synchronous library inside an async def. It freezes the entire event loop. Next, background tasks let you do work after the response has been sent to the client, without making the client wait for it. The canonical example, user registration. The client signs up. You need to save the user to the database, send a welcome email, and update analytics. The client should not wait for an email to be sent before getting their account created confirmation. That's a terrible user experience. With background tasks, we add the email dispatch and stats update to a task queue at the end of the request handler. The return user line sends the 201 response to the client immediately. FastAPI then runs send_welcome_email and update_user_stats after the response is delivered. The client received their response in milliseconds. The email goes out a second later. Both happen correctly. Background_tasks.add_task, func, arg1, arg2. The first argument is the callable. Subsequent arguments are passed to it. Tasks can be sync or async functions. FastAPI handles both. Click. The sequence diagram shows the timing perfectly. The client gets the 201 response before either background task has even started. The tasks run asynchronously in the background. Click. When should you use background tasks versus celery? The decision matrix on the right gives clear guidance. For quick fire and forget tasks, sending a single email, logging a simple event, updating a stat, background tasks is perfect. For long-running jobs that take more than a few seconds, tasks that need retry on failure, periodic or scheduled tasks, or distributed processing across multiple workers, use celery. Background tasks runs in the same process as your FastAPI app. If the app restarts mid-task, the task is lost. Celery persists tasks in a broker. Middleware in FastAPI works identically to the concept we covered in Django, a processing chain that wraps every request and response. FastAPI inherits its middleware system from Starlet. The 3 built-in middleware classes cover the most common production needs. Core's middleware sets the cross-origin resource sharing headers. If your frontend on myfrontend.com calls your API at api.myapp.com, the browser enforces Core's. It checks whether the API explicitly allows that origin. Without this middleware, every cross-origin API call will be blocked by the browser. gzip middleware compresses responses larger than the configured minimum underscore size, here 1000 bytes. JSON responses compress extremely well, often 70 to 80% size reduction. This is free bandwidth saving for every client. Trusted host middleware validates the host header against an allowed list. This prevents host header injection attacks. The custom middleware uses the @app.middleware HTTP decorator. The pattern is do pre-processing, await call_next request to run the rest of the chain and get the response, do post-processing, return. Here we generate a UUID per request for tracing and inject timing information as response headers. The global exception handler overrides the default 422 response format. Here we reshape the Pydantic error payload into a cleaner structure before it reaches the client. Click the onion diagram on the right, shows the layering clearly. The request passes through each middleware layer inward, hits the path operation, and the response passes back outward through the same layers in reverse order. Last added middleware is the outermost wrapper. FastAPI has 3 levels of error handling, and knowing which to use and when is important. HTTP exception is for operational errors, expected conditions during normal application operation. Resource not found, user not authenticated, resource already exists. Raise it with a status code and a detail message, and FastAPI converts it to a JSON error response automatically. The optional headers parameter lets you inject custom headers, useful for www authenticate on 401 errors. Custom exception classes are for business logic errors that span multiple layers. Define a Python exception subclass, write an @app.exception_handler for it, and now any code anywhere in your application can raise insufficient permissions, admin, and get the correct JSON response. This decouples your error definitions from your HTTP layer. Your service functions can raise domain exceptions without knowing anything about HTTP. Request validation error handler lets you override Pydantic's default 422 format. By default, the error structure can be deeply nested and verbose. Here we flatten it to a simple list of field message pairs that's much easier for client code to parse. Click the error flow diagram maps every possible failure mode to its handler. Pydantic validation failure hits the 422 path. An explicit raise HTTP exception returns the HTTP error response. A domain exception routes to its custom handler. Any other unhandled exception becomes a 500. FastAPI supports WebSockets natively through Starlet. A WebSocket connection stays open between client and server, enabling bidirectional real-time communication, perfect for chat, live notifications, collaborative editing, live dashboards. The Connection Manager class is a simple but effective pattern for broadcasting to multiple clients. It maintains a list of active WebSocket connections. Connect accepts the handshake and adds the socket to the list. Disconnect removes it. Broadcast iterates all active connections and sends the message to each one. The WebSocket endpoint is decorated with @router.websocket instead of @router.get. It receives the WebSocket object directly. We first authenticate the user from the token query parameter. You can't use HTTP headers easily with WebSockets, so the token is typically passed as a query parameter or in the initial message. If authentication fails, we close with code 1008, policy violation, and return. Otherwise, we call manager.connect, which performs the WebSocket handshake. Then we enter a while true loop. Wait for a message from this client with receive_text, then broadcast it to everyone in the room. The try/accept WebSocket disconnect catches the disconnect event when the client closes the tab or loses connection, and removes them from the active list, notifying everyone else. Click. The sequence diagram shows a two-client chat. Both connect, the server accepts both. Client 1 sends hello. The server broadcasts it to both Client 1 and Client 2. Client 2 sends hi there. Same broadcast. Client 1 disconnects. The server notifies Client 2. The key point. All of this is handled on a single async thread through the event loop. No threads per connection. Next. This slide is about one of FastAPI's most beloved features, the automatic API documentation that is always in sync with your code. When you create a FastAPI instance, you can pass rich metadata, title, a multi-line markdown description, version, contact email, license. All of this appears at the top of the Swagger UI. Every field, annotation you add to a Pydantic schema, its description, its examples, shows up in the Swagger schema. Every summary, description, and response_description you add to a route decorator appears in the Swagger UI for that endpoint. The responses dictionary lets you document non-default status codes. Declare that your endpoint can return a 401 for Swagger to document it. Click. The generator diagram shows what FastAPI actually does under the hood. It inspects every registered route, reads every Pydantic schema from the function signatures, reads every path and query parameter declaration, and synthesizes OpenAPI.json, a complete OpenAPI 3.1 specification document. That JSON feeds the Swagger UI at /docs for interactive testing, and the redoc renderer at /redoc for clean reference documentation. OpenAPI.json can also feed code generators like OpenAPI-generator-CLI to produce fully typed client SDKs in TypeScript, Go, Java, or any other language, automatically from your Python types. Click the killer feature. It is always in sync with your code. Add a new route, add a new field, change a response model, reload the page and the docs reflect it instantly. You never write OpenAPI YAML by hand. You never fear the docs lying about what the API actually does. That's the superpower. Next. Testing FastAPI applications is straightforward once you understand the async fixture setup. The approach uses http://x.async client with async. This lets us make HTTP requests to the FastAPI app directly in memory without starting a real server. The app processes the request through its entire stack, middleware, routing, dependency injection, Pydantic validation, but the transport is our test harness rather than the network. The setup. A session-scoped test_engine fixture creates an in-memory SQLite database and runs base.metadata.create_all to create all tables. A function-scoped DB_session fixture provides a transaction that is rolled back after each test. Every test starts with a clean slate. The client fixture creates the async client and, critically, calls app.dependency_overrides, get_db equals lambda db_session. This replaces the real PostgreSQL dependency with the test SQLite session. No real database needed. The override is cleared after the test. Test_create_post uses the client to post a new post with valid data and asserts the 201 status code and that the response JSON contains the expected title and an ID field. Test_get_post_not_ found exercises. The 404 path, requesting an ID that doesn't exist, should return 404. Testing both the happy path and error paths is essential. Click the fixture dependency diagram, maps the test infrastructure. The client fixture depends on DB_session, which depends on test_engine. Dependency_overrides is the key linkage between the test infrastructure and the FastAPI app. Click install PyTest Asyncio, HTTPX, and iSQLite. Run PyTest. Asyncio mode equals auto for automatic async test discovery. Add COV equals app for coverage reporting. A healthy FastAPI project targets 80% or higher coverage. Next. Pydantic Settings is the official Pydantic library for application configuration. It reads values from environment variables and .env files, validates them with Pydantic type hints, and provides a typed settings object to your application. The settings class inherits from base settings. Every attribute maps to an environment variable of the same name, automatically case insensitive. Database_URL, str, no default means it's required. Missing it on startup raises a validation error, not a mysterious none, somewhere deep in your code. Database_pool_size, int equals 10 has a default. The type annotation means if you do provide it, it will be coerced and validated as an integer. A string like ABC would fail at startup, not at random runtime. The model_config with env_file equals .env tells Pydantic settings to also read from a .env file in the working directory. Environment variables take precedence over the .env file, so in production, you inject real secrets via environment variables or a secrets manager, while locally you use the .env file. At LRU_cache on get_settings means the settings object is instantiated exactly once. The first call reads and validates all values. Subsequent calls return the cached instance. 0 overhead. Click the .env file on the right is what you commit to your projects, .env.example, the template, while .env itself goes in .gitignore. Never commit real secrets to version control. Click the diagram shows the two sources, .env file and system environment variables both feed into base settings. The cached singleton flows into the FastAPI application. This pattern gives you environment-specific configuration with full type safety and zero boilerplate. Next, let's talk production. This deployment diagram is a real, scalable architecture for a FastAPI application under load. Users connect over HTTPS. Static assets hit the CDN first. CSS, JavaScript, images. API requests go to the load balancer, Nginx, or AWS Application Load Balancer, which distributes requests across multiple Uvicorn workers. Each worker is a fully independent ASGI process, running the FastAPI application. You horizontally scale by adding more workers or more machines behind the load balancer. Each Uvicorn worker connects to the same Postgres primary for write operations. The PostgreScale read replica offloads read-heavy queries, analytics, search, reporting, keeping write load on the primary manageable. Redis serves double duty. It's the caching layer for expensive queries. We saw FastAPI Cache 2 for this, and the session store. Redis is also the Celery message broker. Celery workers run background jobs, sending emails, processing media, triggering webhooks, anything that shouldn't block request handling. They consume tasks from the Redis queue and execute them independently of the web workers. S3, or Google Cloud Storage, holds user-uploaded media files. The CDN is configured to serve directly from S3 for media, so upload retrieval never touches your application server. This architecture scales each layer independently. More web workers, more Celery workers, read replicas. Each can grow without touching the others. Next, let's containerize the application. The Docker file is deliberate about layer ordering for Docker's build cache. We copy pyproject.toml and poetry.lock first, and run the install step before copying application code. This means the expensive dependency installation layer is only rebuilt when dependencies change, not on every code change. We configure Poetry to not create a virtual environment. We're already in an isolated container where that's unnecessary. The CMD runs two things in sequence. Alembic upgrade head applies any pending migrations. Then Uvicorn starts with 4 workers, using UV loop as the event loop. It's a faster drop-in replacement for Python's default event loop, and HTTP tools as the HTTP parser, also faster than the default. Click the Docker Compose file wires up the full local stack in one YAML file. The API service builds from the Docker file and maps port 8000. DB runs official PostgreSQL. Redis runs official Redis Alpine, small and efficient. Celery_worker uses the same application image, but overrides the command to run the Celery worker process. Depends_on ensures the database and Redis start before the API. Click the Compose dependency diagram, makes the startup order clear. Docker Compose up brings up all 4 containers, and the API and Celery worker both connect to the same database and Redis. Click for production. The footnote is important. Add Gunicorn as the process manager wrapping Uvicorn workers. Gunicorn handles worker crashes and restarts. The command is gunicorn main app.-k uvicorn.workers.uvicorn worker. Next, before you ship, go through this checklist systematically. Security. Secret_key must come from an environment variable or secrets manager. Never hard-code it. Debug equals false in production. A FastAPI debug mode can expose internals. HTTPS at the load balancer level. Cores restricted to known origins, allow _origins equals asterisk, is not acceptable in production. Add rate limiting with SlowAPI or at the Nginx level to prevent abuse. Set a short JWT expiry, 30 to 60 minutes, and implement refresh token rotation so users don't get kicked out every hour. Pydantic validates all input automatically, but make sure you aren't bypassing the response model anywhere. Database. Use Postgres with ASYN-CPG in production, not SQLite. Size your connection pool to match your expected concurrency, and Postgres ish equals max_connections. Run Alembic migrations in your CI/CD pipeline before starting the app. Store credentials in a secrets manager. Performance. Install UV loop and HTTP tools. They're significant speed improvements over the defaults. Audit your endpoints for N+1 query patterns. Use SQL Alchemy joined loads. Cache expensive query results in Redis. Enable gzip compression. Operations. Run Gunicorn with Uvicorn Worker as the process manager so worker crashes are recovered automatically. Use Logaru or structlog for structured JSON logging. Greppable, parsable, and essential in production. Wire up Sentry for automatic error capture. Expose/health for your load balancer health checks. Add Prometheus metrics with Prometheus FastAPI instrumentator. Disable the API docs in production with docs_URL equals none. Redoc_URL equals none. There's no reason to expose your API schema to potential attackers. FastAPI has a rich and growing ecosystem. Let's sweep through the major categories. Data validation. Pydantic v2 is the core. Pydantic settings for configuration. Pydantic extra types for additional validated types like color, phone numbers, and payment cards. Database. SQL Alchemy 2.0 is the standard async ORM. SQL model, also by Sebastian Ramirez, combines SQL Alchemy models and Pydantic schemas in one class, eliminating the dual model definition. Tortoise ORM is a Django ORM-inspired async ORM. Beanie is the MongoDB ODM for FastAPI. The drivers, ASYN-CPG, AOMSQL, AOSQLite. Authentication, Python Jose for JWT encoding/decoding. Passlib with bcrypt for password hashing. FastAPI Users is a complete auth solution. Registration, login, password reset, OAuth social logins as a drop-in library. Authlib for full OAuth 2 client and server implementations. Testing, PyTest Asyncio for async tests. HTTPX for the async test client. Factory Boy for test data factories. Faker for generating realistic test data. Tasks, Celery with Redis for production async task processing. ARQ is a lightweight async task queue. AP Scheduler for scheduled periodic tasks. Monitoring, Prometheus FastAPI instrumentator adds metrics endpoints in 3 lines. OpenTelemetry for distributed tracing. Sentry SDK for error tracking. Logaru for beautiful structured logging. Deployment, Uvicorn, Gunicorn, UV Loop, HTTP tools. We've covered all of these. API extras, SlowAPI for rate limiting, FastAPI Cache 2 for response caching, FastAPI pagination for cursor and page-based pagination, FastAPI Mail for transactional email. Next, let's close with the complete end-to-end picture. On the left, the request phase Uvicorn receives the HTTP request, passes it through middleware, the API router matches the path, and dependency injection resolves all declared dependencies. In the center, the processing phase Pydantic validates the incoming request against your input schemas. The path operation function runs, awaiting database queries and cache reads, all non-blocking, all concurrent. On the right, the response phase, the return value passes through Pydantic again for serialization against the response_model, the status code and headers are applied, and the JSON response goes back to the client. At the bottom, the fire and forget lane, the path operation can schedule background tasks or enqueue Celery jobs. Work that happens after the response is sent, without the client waiting. Click 5 key takeaways. 1. Async first. True non-blocking I/O via ASGI and Uvicorn. A single Uvicorn worker can handle thousands of concurrent connections, not threads, coroutines. 2. Type hints everywhere. Pydantic v2 validates all input and output automatically from your type annotations. 422 errors are free. Type-safe autocomplete in your IDE across the entire request/response cycle. 3. Auto-generated OpenAPI docs, /docs, and /redoc update live with your code. Never write API documentation manually again. The docs cannot lie because they are derived from the code. 4. Dependency injection. Clean, testable, composable. Every shared resource, database session, current user, settings, defined once and injected everywhere. Swap any dependency in tests, with dependency_overrides, 0 test-specific code in production paths. 5. Standards-based. OAuth 2, JWT, JSON schema, OpenAPI 3, implemented correctly out of the box. You're not reinventing auth or documentation, you're configuring well-defined standards. Next, and that's FastAPI, from architecture all the way to production deployment. We covered ASGI, Pydantic validation, dependency injection, async databases, JWT authentication, WebSockets, background tasks, testing, Docker, and the full production checklist. If this was helpful, hit like and subscribe for more Python content. Drop any questions in the comments. See you in the next one.